And the second question, naturally we can ask what is the minimum distance in this construction, or at least is it possible to give a lower bound for the minimum distance. And indeed we will see that the answer is yes, and the Hamming distance is bounded below the degree of G minus 2G minus 2. And in order to see that, actually, let me consider a non-zero code word. So that means it is defined, it is derived from the non-zero Weil differential, from the differential space of G minus D. Be a code word of weight of Hamming weight is at least n. So that means such a code word, we know that any non-zero code word of weight m contains m non-zero coordinates. So that means we have n minus m zero coordinates in this case. For some places pi1 up to pi n minus m. And similarly, by using the characterization we gave in our first claim, indeed we can see that omega can be seen a Weil differential of the divisor G minus D minus the sum of this pi j's. Here j is from 1 to n minus m, like we did when we compute the kernel of Brody. And since this is a non-zero Weil differential, just let me remind you quickly the theorem 1.5.17, which tells us that if the degree of a divisor is bigger than or equal to 2G minus 2, the index of specialty is 0. So if we take this, the contraposition of this statement, we can see that the index of specialty is non-zero. So that means the dimension of the divisor space of the divisor is non-zero. Then the degree is less than or equal to 2G minus 2. So that means if this Weil differential contains a non-zero divisor, so that means its index of specialty is going to be non-zero, we can conclude that the degree of this divisor is less than or equal to 2G minus 2. And it's just to compute the degrees. So that means we have degree G, and the degree D is n, because D is the sum of the n distinct places. And this is plus, if we open the parentheses, we can see that the degree of this sum is n minus m, because each Pij are the rational, is the rational place. So, and indeed, this inequality shows us indeed what we want to show, because by the cancellation of n and by replacing the m and 2G minus 2, we can see that the weight of any code word is, minus degree G minus 2G minus 2 less than or equal to m. And we can see that the weight of any non-zero code word is bounded below this quantity, and this shows us indeed the minimum distance is also bounded by degree g minus 2g minus 2. And indeed, thanks to this observation, we can see that for an AG code, which is described in terms of the local components of a Weil differential, we can compute its dimension in terms of index of specialty and its minimum distance is bounded below degree g minus 2 genus minus 2. And like in the AG code, like in the this minimum bound, like for the minimum bound in the AG code, we call this integer the design distance of an AG code C omega d of g. And now actually we will see that there's a close relation between the AG code, which is described in terms of the evaluations of the functions of the Riemann space of G at these distinct places which are supporting D, and AG code, which is described in terms of the local components of a Weil differentials. More explicitly, in theorem 2 to 8, we will see that they are dual to each other. And here by duality, we mean the dual of a linear code, and this dual determined with respect to the standard inner product on FQ to down. And in order to see this equality, first we see that the left-hand side lies in the right-hand side. So that means for if we consider any code word from an AG code C omega d of g, with omega is bigger than or equal to g minus d, our first claim, actually our main claim, let me write it, claim 1, is to see that this n-tuple is orthogonal complement to the n-tuple in the AG code of CI of the NG. So that means the functions x are from the Riemann space of G and evaluated at PIs. And indeed, so in order to see this equality means that, but if we write this, the definition of the standard inner product, indeed, essentially, we want to see that this sum is equal to 0. And in order to see this equality, indeed we investigate another statement for this product. So the question is that, is it possible to write this product again in terms of the local components of a function? And indeed we will see that. Let me write it as claim 2. For a given rational place P and the non-zero Weil differential omega, who can have pole at P of order at most 1, and for a function f which has no pole at P. So let me note that we are in this special case because we are interested in the Weil differentials from the differential space D minus G. So that means its divisor is bigger than or equal to D minus G, particularly its valuation at PI's. So PI's are the rational places in this case, of omega is bigger than or equal to minus 1. So, I mean, this is the VPI valuation of G minus D at PI, and this is going to be minus 1. And if, so that means the Weil differentials here satisfies this inequality. And similarly, since we are working with the functions from the Riemann space of G, that means the poles and the zeros of these functions are described in terms of the places in the support of G. But since G and D has a disjoint support, we know that VPI of X is bigger than or equal to 0 at any place which lies in the support of D. So for the Weil differentials and the functions in our setting, we always have these conditions. And if this is the case, then under these assumptions, under these conditions, we can see that indeed each term which appears in the sum, or the local component of the Weil differential at P of 1 times XP, this is a product in the finite field, indeed can be written as omega P of X. Here X denotes the same function. And indeed, we can prove this equality just by writing X as A plus Y. So this is possible because by the assumption we know that VP of X is bigger than or equal to 0, and like in the previous case, we know that this implies or this gives us characterization about X lying in OP. And since the degree P is 1, we can write X as A plus Y. More explicitly here, we can also observe that A denotes the evaluation of the function X at P. And here function Y has zeros at this given places P. And thanks to this representation, if we take the local component of the Weil differential and by its linearity, we can see that in this right-hand side, can be written in this form. So simply here, again, we will observe that this quantity is 0 because we know that by the assumption, the valuation of omega is bigger than or equal to 1, if and only if VP of x is 0 for all functions that have zeros at p of order at least 1. Like again, in prop 1, I think it was prop 173. This is the statement, prop 173. And in that, by replacing a by xp, we can see the desired equality. So that means we can rewrite this statement. We can restate, hence we can restate claim 1 as VPI of 1, PI is 0, I from up to n, as I claim 2, is VPI of x is 0. Here PIs are the distinct places. And indeed, if we are able to see that, this sum, if this sum is equal to the sum of these local components over all places, indeed, from last week we know that this Weil differential can be written as a sum of its local components over all places. And since any Weil differential is vanishes on the principal addends, this side is going to be 0. So here the only trick is to see that for places which are disjoint from this given distinct place PIs, we need to see that VP of x is 0. So that means this sum indeed can be determined by only checking these local components at this given PIs. So let me write it as this question by claim tree. And our purpose is to see that for any places which are different from PIs, we have this equality. And for this purpose, let me first observe that if we consider a function from the Riemann space L of G, indeed what we want to see that first for these places, VP of x is bigger than or equal to minus VP of omega, and in order to see this inequality, it's just enough to consider, okay, we are working with the functions from L of G, so that means the principal divisor of x is bigger than or equal to G, and since we are working with the Weil differentials from this differential space, we know that omega is bigger than or equal to G minus D. And since G minus D I think I made a mistake here. By using this, let me say for the discussion session, it can be better. Discussion session. And by using these facts, in that we can see that VP of X is bigger than or equal to VP of W. But there's only one thing I want to point out here. In this case, we need VPI of omega is 0, because if it is -1, and if X has no pole or zeros at these given places, because this can be also case for the Weil differentials in this differential space or the functions L of G, we can't get this inequality. So we need to be sure that this inequality holds for only places P, and this is not the case if we choose this place among these rational places. And if this is the case, again, by prop 173, we can conclude that this local component of X is 0, because having no poles, VP of omega is bigger than or equal to VP of X, so this denotes the integer. Can be characterized in terms of the local components of Weil differentials of the functions. Obviously, their evaluations satisfies this inequality. And thanks to seeing this claim 3, indeed, we complete the inclusion, the left inclusion. And now it is okay if we have two vector spaces, one is included in the other side, and if we are able to see that they have the same dimension, indeed we can conclude that indeed they are the same vector space. So in this case, it is sufficient to show that they have the same dimension. And we can easily verify that the dimension of the AG code C omega of D and G can be computed in terms of the index of specialty and by the definitions of the index of specialty. And with these cancellations, we can see that this integer indeed gives us also the dimension of the dual code of CL of D and G.